Inside every single living thing, there are these microscopic machines called proteins. They're incredible. They build their bodies, they digest our food, they fight off invaders, they do pretty much everything. But to really understand how they work, we first have to solve this huge puzzle. What do they actually look like? So in this explainer, we're going to crack the code and uncover this seriously ingenious method scientists have developed to map this invisible world.
I mean, think about this. Proteins are thousands of times smaller than the wavelength of visible light. That makes them totally invisible to any standard microscope. So how on earth have scientists managed to create these detailed 3D maps of molecules we can't even see? It's a real-deal scientific detective story.
And trust me, mapping them is everything. Because for a protein, its intricate three-dimensional shape directly dictates what it does, its function. You change the shape, you change its job. So knowing that shape, well, that's the key to understanding life itself.
Okay, so let's really dig into that fundamental principle. You know how a key needs a very specific shape to fit into a lock? It's exactly the same idea, just on a molecular scale. A protein is folded into this one precise shape to do one specific job.
It's been put perfectly. Every single protein has a distinct structure, basically custom built for its own biological function. There's no one-size-fits-all here. This incredible specificity is what allows for all the complexity of life. So the big question is, how do we see these custom shapes? Well, for that, we're going to need some special tools.
All right, so our first major technique in the toolbox is kind of like taking a molecular photograph. But wow, is it way more complex. It's called X-ray crystallography, and it was the very first method that allowed us to truly see a protein's atomic structure.
Okay, think about it. To see something as tiny as an atom, you need a wavelength of light that is just as small. And that's where X-rays come in. The basic idea is to shine a beam of X-rays at a protein and see how they scatter. But there's a catch. First, you have to get the proteins to hold perfectly still. So, the whole process boils down to 3 key steps. First, and this is the really tricky part, you have to convince millions of these protein molecules to line up perfectly into a crystal. Then, you shoot that crystal with a powerful X-ray beam. As the X-rays pass through, they get deflected by all the atoms, creating this unique fingerprint, a diffraction pattern.
And I really can't overstate how hard that first step is. One scientist captured the challenge perfectly, comparing the process to holding together a stack of bowling balls with cellophane tape. It's an art form as much as it is a science, and for a lot of proteins, just getting them to crystallize can take years of work.
Okay, so you've done the hard work. You've somehow managed to make a crystal, and you've captured that pattern of dots. Now what? How do you turn that abstract pattern into a detailed 3D structure?
Right? This pattern you're looking at? That's the raw data. It might just look like a bunch of spots, but every single one of those dots contains precise information about where the atoms are inside the protein crystal. It's basically a treasure map, but it's written in a language we can't read directly.
The problem is, we don't have a lens that can actually focus X-rays into an image, so we have to get clever. We use a powerful mathematical tool instead. A process called a Fourier transform lets a computer act as a computational lens, taking all that scattered data from the spots and starting to reconstruct an image from it.
And what pops out of that computation is this, a 3D electron-density map. Now, it's not the final structure yet, but it's a super important step. Think of it like a fuzzy cloud that shows where the electrons in the protein are most likely to be. The denser the cloud, the more atoms are packed in there.
And then comes the final, painstaking step. Scientists meticulously fit the known amino acid sequence of the protein into that electron cloud, kind of like building a model ship inside a bottle. And this is the amazing result. It's the first ever structure of a protein like this to be solved, myoglobin. A feat by John Kendrew that was so groundbreaking it won him a Nobel Prize. Just a beautiful, static snapshot of a protein.
But wait a second. Proteins aren't static. They're not just sitting there like little statues. They move, they flex, they breathe. A single snapshot is great, but what if we want to see the movie? For that, we need a different tool, nuclear magnetic resonance, or as everyone calls it, M&R. So let's put our 2 detective tools side by side. Crystallography gives us an incredibly high-resolution but totally static picture, and it requires the protein to be locked up in a crystal. NMR, on the other hand, works on proteins in a solution, which is much closer to their natural home in our cells, and it can actually capture their movement. The trade-off?
It usually works best on smaller proteins.
So how does NMR do its magic? Well, you place the protein solution in a crazy strong magnetic field, and you poke it with radio waves. By analyzing the signals that come back from atomic nuclei like hydrogen, scientists can measure the distances between different atoms. That gives them the clues they need to piece together the protein shape.
And this is what you get from NMR. It's just beautiful. It's not one single structure, but a whole family of structures that all fit the data. This collection represents the protein's natural flexibility in solution, what some people call its molecular breathing. It's a much more dynamic and probably more realistic view of the molecule.
Okay, so we've got two totally different methods. One gives us a static picture from a crystal, the other gives us this dynamic view from a solution. Are they even telling us the same story? Do they agree?
And the answer, which is a huge relief to scientists, is a big yes. When the same protein structure is solved by both X-ray and NMR, the results agree remarkably well. This gives scientists a ton of confidence that the structures they're seeing are accurate. The bottom line is, these two methods complement each other beautifully.
And these methods have just opened up a whole new world, showing us this incredible diversity in protein architecture. Just look at myoglobin here. It's made of 78% alpha helices. You can think of those like coiled springs. Now look at chymotrypsin. It has almost no helices at all. Instead, it's built from 45% beta conformations, which are more like folded sheets. We're talking completely different blueprints for completely different molecular machines.
And this right here just drives that point home visually. On the left, you've got myoglobin, packed with those coiled spring alpha helices, which is perfect for its job of storing oxygen. Then on the right, you have lysozyme, an enzyme that literally attacks bacteria, and it has a totally different mix of shapes that creates a specific groove to do its job. It's perfect. Form follows function.
Okay, so let's tie this all together. What's the bottom line? The 3D shape of a protein is everything. It determines what it does. We use powerful tools like X-ray crystallography to get a high-res static picture, and NMR to see it in motion. And this isn't just for textbooks. This is the foundation of modern medicine. By knowing the exact shape of a virus's protein, for example, we can design drugs that fit into it perfectly, like a key breaking off in a lock, jamming its mechanism, and stopping a disease like HIV cold. We have literally cracked the code for seeing the invisible engines of life. The question that's left is, with this incredible power to visualize the molecular world, what profound challenges in medicine and biology are we going to tackle next?